Let's dive right in. We're about to go on a journey to the absolute smallest scale you can imagine, to really understand the fundamental building blocks of, well, literally everything. So let me start by asking you a question. What's the one thing that connects you, the phone you're probably holding, and a gigantic gas planet like Jupiter? It sounds kind of like the beginning of a weird joke, right? But the answer is actually at the very heart of all chemistry. The answer is, they're all made from the exact same stuff, these tiny, fundamental particles we call atoms. Honestly, the best way to think about them is like the universe's ultimate Lego bricks. From just a handful of these little bricks, you can build absolutely anything, from a star to a sandwich. So where did this incredible idea even come from? Well, our story really kicks off in the early 1800s with a guy named John Dalton. He's the one who laid out the very first real scientific theory about the atom.
Dalton's first big idea was, for its time, revolutionary, but also beautifully simple. He basically said that every element, like gold or oxygen or iron, is made up of these incredibly tiny, indivisible particles that he called atoms.
And he didn't just stop there. He built a whole framework around this. His theory had four main points. First, everything is made of atoms. Simple enough. Second, all atoms of a particular element, let's say carbon, are exactly the same. Third, atoms are indestructible. Chemical reactions don't destroy them, they just rearrange them. And fourth, when elements combine to make something like water, their atoms always join up in the same, simple, whole number ratio.
For a long time, Dalton's theory was pretty much the final word on the matter. The atom was the smallest thing, period. But then, science delivered a major plot twist.
You see, in Dalton's mind, an atom was kind of like a tiny solid bowling ball. You couldn't break it down any further. That was it, the end of the line.
It was a really powerful idea, and it explained a ton of stuff that scientists were seeing. But the question that just kind of hung in the air for decades was he actually right? Was that the whole story?
And the answer, as it turned out, was a big fat no. Around the turn of the 20th century, there was this series of bombshell discoveries that just completely changed the game. First, J.J. Thomson found this teeny-tiny negatively charged particle called the electron. Then, folks like Becquerel and the Curies discovered radioactivity, which proved atoms weren't always stable. They could actually spit out particles and energy. And then came the big one, Ernest Rutherford's gold foil experiment. It showed that the atom was mostly empty space with a tiny, dense, positive center he named the nucleus. Just like that, Dalton's little bowling ball model was completely shattered.
Okay, so if the atom isn't a solid ball, what in the world is actually going on in there? Well, let's meet the three main characters that make up every single atom in the universe.
First up, we've got the proton. It's got a positive charge, and it lives inside that central nucleus. But here is the absolutely crucial part. The number of protons an atom has is its identity card. It defines what element it is. An atom with one proton is always hydrogen. One with 6 protons is always carbon. No exceptions. That's the rule.
Next, let's meet the proton's roommate in the nucleus, the neutron. And just like the name suggests, it's neutral, no charge whatsoever. Its main job is to add mass. It's just as heavy as a proton, and to help keep all those positive protons from flying apart. You can think of it as the heavy, stable friend keeping everyone together.
And finally, we have the electron. It's got a negative charge, and it's buzzing around the nucleus in this kind of blurry cloud. Now, electrons are incredibly tiny, but they are the true social butterflies of the atomic world. They're the particles that actually interact with other atoms to form chemical bonds, which is basically what makes all of chemistry, well, happen. This side-by-side look really breaks it down perfectly. You've got your positive proton, your negative electron, and your neutral neutron. But check out the mass column. Protons and neutrons are the heavyweights, with a mass of about 1. The electron, wow, it's almost 2,000 times lighter. It's so light that when we're calculating an atom's mass, we usually just ignore it. It's like a speck of dust on a bowling ball. So, what happens when those little social butterfly electrons decide to leave home? Or maybe invite a friend over to stay? Well, the atom suddenly gets an electrical charge, and a bit of an attitude.
This charged-up atom is called an ion. See, an atom is normally neutral because it has the exact same number of positive protons and negative electrons. Their charges cancel out, but if you upset that balance by either losing or gaining an electron, the whole atom gets a net charge. Now, here's the key. There are 2 types of ions. If an atom loses a negative electron, it now has more positive protons than negative electrons, right? so it gets an overall positive charge. This is called a cation, and a silly way to remember it is that cats have paws, so cations are positive. I know, it's cheesy, but it works. And if an atom gains an extra electron, it becomes negatively charged, and we call that an anion.
And here's a great little cheat sheet for you. Generally speaking, if you look at the periodic table, the metals over on the left side, they like to give away their electrons. They're givers, so they form positive cations. The nonmetals over on the upper right, they're electron greedy. They love to gain electrons, so they form negative anions.
Okay, let's put this all together. We've met atoms, we've met the particles inside, and now we've met ions. So let's see how they all come together in a real-world example that's probably sitting in your kitchen this very second, table salt.
So here's the play-by-play. We start with a sodium atom. Now it's a metal from the left side of the table, so it's very generous, and it happily gives away its outermost electron. By losing that one little negative charge, it now has 11 positive protons but only 10 negative electrons. So it becomes a positive sodium ion, or Na+.
Of course, that electron has to go somewhere, and hanging out nearby is a chlorine atom. It's a nonmetal from the right side of the table, so it is very greedy for one more electron to feel complete. It snatches up the electron that sodium just gave away. Now it has 17 protons but 18 electrons, which gives it a negative charge. It's now a chloride ion, Cl-.
And what happens when you put a positive charge right next to a negative charge? You know this one. Opposites attract. The positive sodium ion and the negative chloride ion are now powerfully drawn to each other, and they lock together, forming what we call an ionic bond. When you get millions and millions and millions of these pairs all stacking together, you get the crystal structure that we know and love as sodium chloride or just plain old table salt.
So there you have it. From subatomic particles to the salt on your food, it all comes down to these simple rules of attraction and how electrons move around. We've seen how combining atoms in new and exciting ways builds literally everything around us, which leaves us with one final, pretty mind-blowing question. What happens when we do the exact opposite and try to split them apart?